Swayam Prabha. Digital India. Educated India.
So far we have looked at this field of study called game theory, which looks at rational behavior in multi-agent scenarios. Then we looked at a host of popular games and got some history about which games are played well by machines and which are not played well by machines. In the subsequent lecture, we will focus on simpler games. These are called board games, and we will see how they are modeled as game trees and what are the algorithms used for playing these games. So, board games are essentially two-person games, in the sense that they are played between two players. So, chess is an example, checkers, go, or the humble cross and knots which children play. All these are examples of board games in which there are two people involved. These are zero sum games, where one side wins and the other side loses. The total payoff, as we have studied in zero sum games, is 0, or the game can end in a draw, which is, and they get 0 points for that, and as we will see shortly. These are complete information games, where both players can see the board position completely and they can see the moves available to the opponent as well. So, they know exactly what the other person can do and take that into account in their own strategy formation. These are typically alternate move games, where each player makes a move turn by turn, though under certain conditions one player may be allowed more than one move, or what can be called as a compound move. So, if you have played the game of checkers, you know that you can capture 2 coins at one time, or if you have looked at reversi or Othello also as it is called, then if the opponent does not have a move, you get a second move. But typically they are alternate move games, that you play a move, I play a move, and so on. And they are deterministic games. There is no element of chance of any kind involved in this. So, as you can see that they are the simplest kind of games that we can consider, but in this small set are games like chess and go, which have fascinated us for centuries together. It does not include games like backgammon, which is a throw of dice, or card games like poker and bridge, or games like Scrabble, where there is an element of chance as to which letters you get and you do not know what the opponent is opening. These are much simpler games, 2-person, zero sum, complete information, alternate move, deterministic games. So, let us see how to tackle such games. Once you know the rules of a game, then you can construct a corresponding tree, which is called a game tree. In this tree, there are 2 players involved. Remember, it is a 2-person game, and the 2 players are signified by different ways of drawing the node, and it is a layered tree in which we always look at the game from max's perspective. The one player is called max, the other player is called min. Typically, we draw the max as a square and min as a circle, and it is a layered tree in the sense that at the first level max has to make a choice, then based on the choices of max at the second layer min makes a choice, then based on the choice of min at the third layer max again makes a choice, and so on and so forth. And all the games that are possible are represented as paths in this game tree. So, max and min choose alternately, max makes the first move, min the second, and so on. We always see the game tree from the perspective of max, because if we imagine that we are going to write a program for max, the leaves of the game trees are labeled with the outcome of the tree. So, once a game has ended, you know what has happened. So, W stands as a win for max and loss for min. So, for example, here is a leaf which is labeled W, which means that if the game that is played is as follows, then Max would have won the game. The label W stands for win and the win is for Max. L stands for a win for Min and a loss for Max. So, if we had ended up in a leaf node which is labeled L, that would mean that Min has won the game. And we have the third outcome possible, which is for example, here, which is draw. D stands for a draw, which means neither side has won essentially. So, to kind of quantify the payoffs, we can sometimes label them with +1 for Max, -1 for Min and 0 for a draw. So, you can see that the total payoff is, if one of the side wins, it is +1 and -1 for each player. You have to add them up, and if neither side wins, then it is a draw. They both get 0 points. You can also see why Max is called Max, because Max is trying to reach the score of +1, which is the maximum of the 3 possible outcomes, and Min is called Min because Min is trying to choose the smallest value in the game, which is -1. Now, what happens when a game like this is played? Now, remember that we have said that we are concerned with rationality here, that we assume that both the players are perfectly rational, they are perfectly able to think about the consequences of their actions, they can look ahead and analyze the complete game tree. So, given a board game like this, we can determine what is the Nash equilibrium for this particular game, and which is when both the players play perfectly. So, as we said, the leaves are labeled with the outcome of the game. When both players are rational, the value of the game becomes fixed, because both players make the best move at every stage. That value is known as the minimax value. It is the outcome when both the players play perfectly, and the minimax value of a game or a game tree can be computed by applying the minimax rule in a bottom up fashion, which means you start from the leaves and you go up towards the root of the game tree. The minimax rule is as follows, that if J, the node that you are looking at, is a max node, then backup values from its children as follows, that if a W node is available, you back it up or +1 as the case may be. If W is not available, you back up 0 or D, else you back up L or -1, which means that if there is a move in which Max can win, Max will make that move, and therefore, the value of that game will be W. Otherwise, Max will make a move in which the game becomes a draw. So, the value of that node J will become 0, backed up value. Otherwise, there is no option but to lose the game. Likewise, for Min, you back up in the reverse order, that if you are a Min node, if you are looking at if J is a Min node, then from the children of J, you back up L if possible. Remember, L is a loss for Max and a win for Min, and Min is also trying to win the game. So, L also corresponds to -1 that we said, and that is why we said that Min player is called so, because it chooses the minimum value, which is -1 in this case. If it cannot get a value of -1, it will also, like Max, settle for a draw. So, the second choice is always 0 or draw for both the players, and the third choice is to lose the game, in which case it will have to back up a value of W, which is a win for Max, but a loss for this thing. So, at each layer we can do this backup of values, and once we do this, we will get the minimax value of the game tree. So, let us see this process on the small game tree that we have constructed. Now, remember that the game tree encapsulates all the rules of the game. You have constructed the game tree by looking at the game rules and deciding what are the moves for Max and what are the moves for Min. We have not labeled the moves in our game tree, but you can imagine that each move has a label. For example, pawn to king 4, or place a cross at a particular square in cross and knots, whatever the case may be. But eventually we have a game tree where there are a set of choices available, it is a layered tree, and now we are trying to find out what is the minimax value of the game tree, and we will do that by applying this backup rule in a bottom up fashion. We will start with the leaves and move up towards the root of the game tree, and having done that, we will know that if both the players play perfectly, what is the outcome of the game. So, let us look at this for the small game tree that we constructed. As we said, we will start doing this process in the from the bottom up fashion. So, if you see this node at the lowest internal node that we can find, it has two choices, one is +1 and the other is 0. Now, clearly this is a min node, it will choose the minimum of the two values. So, it will choose a value of 0. Its sibling has two choices, which is -1 and 0. So, it will choose -1, and in this fashion we will back up the values, and eventually all the nodes will get a value. So, max chooses the maximum child value and min chooses the minimum child value, and this is the process that we are seeing now. First, the nodes at the lowest layer, the internal, are being backed up, and then once they have their values are backed up to the next higher layer, and so on essentially. So, you can see that at each stage min is choosing the minimum of all possible values and max is choosing the maximum of all possible values. Sometimes, as you can see, min is forced to choose +1, which is a win for max, and that happens for example, here when all the children of that particular min node are labeled as +1. So, it has no choice but to back up a +1. So, this small game tree that we constructed, somewhat random tree, is such that if both the players play perfectly, then max will win the game essentially. Obviously, if a game tree was so small and you could analyze it completely, it would be no fun to play the game, because you are assuming that both the players are perfect. But as we will see, most games are not so small, and so they are not so easy to analyze, which is why games like chess and Go still fascinate us. But a game like tic-tac-toe or cross and knots, which you might remember, is a game which is played on a 3 by 3 square, and essentially it involves placing a cross or placing a knot and then placing a cross and a knot, and so on and so forth. Now, those of you who have had the chance of playing this game in your childhood, you would know that the value of this game is 0, which means that if your opponent is playing well, if both the players are playing perfectly, then the game will always end in a draw, which is why as you grow older you lose interest in the game, because you know that there is nothing much which can be done. But that is not the case for chess, as we will see. You could have used the nomenclature of the three labels win or draw or loss, W, D or L. So, max's first choice is W, if not W then D, else L, and likewise min's first choice is L, if not D, else W. So, this tree that we are looking at now, it is just relabeled. You could have just substituted -1 with L, 0 with D and +1 with W, and you would have got the same tree. But very often as human beings, we like to look at the words like win, draw, loss, and because that is how we think of in terms of the game. But the two notations are equivalent. As we move forward, we will see that we will have a tendency to move towards the numerical notation for reasons that we will see, which will become clear as we go along. Now, there is a notion called strategy. Remember that when we talked about game theory, we said what is the strategy for each player? It is the rational choice that you can make. Now, games that we talked of like prisoner's dilemma, you had to make only one move. So, you had to simply have a device of whether you will betray your partners in crime or whether you would cooperate with this thing. So, you have to make only one move, but in multiplayer games you have to make a sequence of moves. You make a in a multi move game, you make a move, then opponent makes a move, then you make a move, and then opponent makes a move, and so on. So, in such a scenario, what is the strategy? So, we define a strategy for a player as a subtree of the game tree, such that it completely specifies the choices for that particular player. So, once I have looked at a game and say in this board position, this is the move I will make, then you are freezing your choices. But because you do not know what the opponent will do, you cannot decide for the opponent. So, you have to consider all possible choices for the opponent. So, this is how a strategy is constructed, and we are again going to look at it from the perspective of Max, because we imagine we are writing a program which will start playing the game. So, here is a small program for constructing a strategy for Max. You start traversing the game tree starting at the root, go down level by level. If it is a max node that you are looking at, or if it is a max level, then choose one branch below it. If it is a min node you are looking at, if it is a min level, then you choose all the branches below it, and then finally you return the subtree that is constructed. Now, this represents one strategy for Max. Likewise, you can make many choices. So, remember that when you are choosing one branch at any node, then you have a choice point, and this is the place where Max has to decide as to which move to make. So, Max will have a set of strategies corresponding to any game tree. So, here is a example of our game tree. We have two strategies for Max. One is, let us call it a red strategy, and let us call the other a green strategy. Remember that strategies are subtrees of the game tree. So, what you see is a complete game tree, and what you see in red is a subtree, and what you see in green is another subtree. So, these are two different possible strategies for Max. Obviously, there can be other strategies as well. At every place that we chose move for Max, for example, this one, you could have chose a different move, and that would be a different strategy. Now, what do these two strategies achieve for Max? You can see that these are the leaves in the two strategies which are colored, and in the case of the green strategy, because now the choices are left to min. Remember that Max has frozen Max's choices, and the game will be decided by what min does. So, clearly if you look at the green subtree, it has two kinds of nodes, either a win for Max or a draw for both of them. There is no L labeled leaf here, and so the best that min can do in this strategy, if Max were to choose the green strategy, it would drive the game towards a draw. So, if Max makes this move, then min can make this move to take the game to a draw, or min can also make this move, which will, in which Max has said he will make this move, and then min can again drive it to a draw, and likewise for the third node, which is at the bottom here essentially. So, clearly min will not drive the game towards a node labeled W, because min is also trying to do the best. In this particular, if Max has said that this is my strategy, then min can say, okay, I will accept a draw from you. On the other hand, the red strategy has all the leaves which are labeled with W essentially. So, min has no choice but to lose the game, and we saw when we analyze this particular game tree that the minimax value of this game tree was +1, or it was a win for Max, and max can achieve that by choosing a winning strategy. A winning strategy is a strategy in which all the leaves are labeled with W for max. So, ideally the task of max is to analyze the game tree and come up with a winning strategy. And we will focus a little bit on this, especially for game trees which are much larger than this particular small game tree. Now, if both the players have chosen the strategy, remember min can also choose a strategy likewise. In a strategy for min, you would make one choice for min node and all choices for max node. So, min can also analyze this particular game tree and say that this is my strategy. So, let us say now the red subtree is a strategy for min. So, the red strategy is for min, which means, so there is a common edge between. So, the green strategy is the strategy for max, the red strategy is the strategy for min, and the intersection of these two strategies is going to be a path which is depicted by double lines in this tree, and this path which is the intersection of the two strategies is the game that will actually be played if both the players have frozen their strategies. So, remember that the red subtree is a strategy by min, the green subtree is a strategy by max, and this path that we have shown is the intersection of the two strategies. These are the edges which are common to both the strategies. So, once the two players have frozen the strategies, we know what is the game that will be played and what will be the outcome of the game as well. Now, let us have a brief look at complexity of games, and when we say complexity of games, we mean the size of the game tree. Of course, this is complexity not in terms of the order notation that we use in computer science very often, where the complexity is in terms of some parameter like the size of a matrix, for example. But here the size of the game is fixed, in the sense that the board is fixed. We simply want to have a estimate of what is the size of the game tree, and this is what we mean by complexity of a game tree. So, the simplest possible game is tic-tac-toe or cross and knots that we have seen a little while before. You know that the first player has 9 moves, you can place a cross in any of the 9 squares, and then the second player would have 8 moves and so on. So, we are not kind of taking care of symmetries which may or may not be easy to handle in a program. But in the worst case, you can say that the first player has 9 choices. In practice, if you take into account symmetries, the first player will have only 3 choices, either a corner or the center or a side. But then we want to simplify matters. So, we say the first player has 9 choices, second player has 8 choices and so on, and the total possible games will be 9 factorial, which, as we have discussed, we already know that always ends in a draw when both the players are playing perfectly. But let us look at the game of chess. Now, the branching factor of chess is also variable. So, if you know the first player, white in the case of chess, can make 20 moves. It can make 8 pawn moves, moving them forward 1 step, another 8 pawn moves, moving them forward 2 steps, that is 16, and it can move each of the knight forward and left and forward and right. So, that is 4 moves. So, the total moves are 20. Any program which searches the entire tree will have to consider all possible 20 moves. So, human players do not tend to do that, we always go through a process of learning in which we figure out that certain openings are good, and in fact, there are books available on chess like modern chess openings, which tell you what are the different kinds of openings that have been used by good players. But as the game progresses, the board opens up, because as pawns move forward, the pieces behind them, for example, the queen or the rook or the bishop, they become more mobile and the number of moves becomes larger and larger, and it increases towards what is called as the middle game. Then towards the end game, when the number of pieces start declining because many captures are taking place, the number of branching factor again goes down a little bit. It has been estimated that on the average, the branching factor in the game of chess is 35. So, on the average there are 35 choices that a player can make, and typically a game is 50 moves long essentially. So, if you take these average numbers, then you can imagine that there are 35 raised to 50 possible games, and which translates to 10 raised to 120 possible games. Now, this 10 raised to 120 is a number that we cannot even begin to comprehend essentially. If you just think of the fact that the number of fundamental particles in the entire universe is estimated to be 10 raised to 70 or 10 raised to 80 or something, and if each of these fundamental particles was a supercomputer looking at whatever you want, 10 billion moves a second, 10 trillion moves a second, you can see that there would still be a factor of 10 raised to 30, 40 remaining, and that would translate into millions and millions and millions of centuries. So, clearly we cannot analyze the full chess tree, and therefore, we do not know what is the value of a chess game, which means that we do not know whether if both the players are playing perfectly, whether white will always win, or whether the game will always be a draw, or whether black will always win, and that is why chess is still a fascinating game for us, unlike tic-tac-toe or cross and knots, which we know will always be a draw. Now, we know that chess has been, it is not been solved in the sense we do not know the value of the game, but we have programs which are good enough to play to beat the best humans, and that started off in 1997 when IBM's Deep Blue program beat the world champion Garry Kasparov essentially. Now, the next board game which for many years was considered to be difficult for machines to tackle was Go, because Go was played on a 19 by 19 chess board. So, in some sense Go and tic-tac-toe have a similarity in that in Go, if you remember the figure that we had seen, you had to place either a black coin or a white coin on the board, and there were 19 by 19 choices in the first place, and you can imagine that the size of the branching tree was really humongous. And for a long time people thought that Go is difficult for computers to beat humans at, and people said that Go involves a different kind of reasoning, which some people associated with Zen reasoning, where you kind of look at the chess board or a Go board for a long time and somehow the right move pops up. But as history has shown us, the program AlphaGo written by DeepMind, it did beat the world champion in this is a mistake, in 2016. So, Go is also a board game which has been tackled by machines essentially. How do these programs work? As we have just seen, most interesting games, they are too huge for to be analyzed completely. The chess tree has about 10 raised to 120 possible games. The Go game has much more, and therefore, you cannot analyze the game completely. So, now we will start focusing on how to write programs to play these games, and as we will see, these programs will rely on a limited look ahead, that you do not look ahead till the end of the game, but only for a few moves ahead. And if you do, and when you do that, you apply what we will call as an evaluation function, which is going to be a static function, which will look at a board position and give it a value essentially. So, this will be a value which would signify whether the game is good for player max or whether it is good for player min and so on. And we would use this evaluation function to guide our game playing program, and we will do that in the next session onwards, and we will look at a few algorithms for playing real games. So, see you the next time.